So welcome everyone to CTNT 2026. This, by the way, is the 10th year anniversary of CTNT. We've been doing this since 2016. Keith and I did a run of CTNT in 2014, yes. And that was just a one-day conference, and that was like the test to run something like this in full scale. So in any case, welcome to UConn and welcome to CTNT. And my mini course is on elliptic curve cryptography, which is an excuse to talk about elliptic curves. But there's a lot of like very interesting things that algorithms have been developed around elliptic curves that have to do with cryptography. So I thought I would take a chance to talk about those. So my plan for this mini course is, well, I'm going to give you a little bit of a history of how this came about, then also an introduction to elementary number theory, just the very basics of elementary number theory that are used when we work with elliptic curves, and then an introduction to elliptic curves, and then we're going to start doing cryptography. Many of the methods that were developed for elliptic curves are analogs of methods that were known to work for Z modulo P. So what I'm going to do is many times I'm going to start by telling you, like, this is how Diffie-Hellman works, modulo P. Let's now invent it for elliptic curves. And then you'll see that, in fact, all the ideas of these methods are very simple. Like the actual methods, they have very simple functionality, but they end up being very robust. Robust enough that we are still using them until somebody actually develops a serious quantum computer, and then we're toast. Okay, so we're going to talk about elliptic curve cryptography, and that will but not completely, because so as I said in the messages, my lectures, I have 4 lectures that I'm giving, and then I'm outsourcing 2 more lectures. In that, Christelle Vincent will give a lecture about quantum computing and quantum cryptography in particular. So I think she will talk about what things we can break if we had an actual working quantum computer. And then Sarah Arpin will talk about isogeny-based cryptography, which is again based on elliptic curves. And that one is, as far as I understand, quantum safe. So we still have hope that elliptic curves will have a future in cryptography, whether we have a quantum computer or not. Okay. And we are going to talk about factorization algorithms, because some of the methods that are used in cryptography depend on the fact that factorization is very hard. Factoring a very large number is a very hard problem. But yet again, elliptic curves help in factoring numbers. So elliptic curves can help you do cryptography, and they can help you break cryptography. So they are the solution to everything, which is why you should be a number theorist. Okay, so here's some brief history of cryptography. You might have played around with Caesar ciphers. So those are some of the very early methods that, well, there is maybe hieroglyphics, and Egyptian hieroglyphics may be an even earlier version of cryptography, but some actual methods where somebody was trying to hide a message appeared in Caesar ciphers. Much later, these sort of ciphers, of course, I assume that people tried and knew how to try to break them, but how to break them sort of theoretically didn't appear in text until like like in the 800s. In the 800s, Al-Kindi introduces frequency analysis, that if you have a large text that has been encoded with, say, a Caesar cipher, you can figure out what's the code that has been used. But you can see the cryptography was very slow, a very slow start. Some other, like 700 years later, Belasso, who unfortunately didn't get much of the credit for this, but Belasso and then much later Vigenère invented a new type of cipher. which is now called the Vigenère cipher, which does resist frequency analysis because the same letter doesn't get, if you set it up right, the same letter doesn't get encrypted with the same character, every time it changes. So that frequency analysis, the frequency analysis is based on like what's the most common letter in your alphabet. Then you check what's the most common symbol in your text, and then you can figure out what letter that is. But if you are changing what character represents what letter all the time, then it resists frequency analysis. Now, with the wars, unfortunately, trigger advances in cryptography. The one-time pad is just, you have a pad of numbers. I have the exact same pad of numbers, and then you travel to Europe to be a spy, and I keep mine. And then we're using, every time we communicate, we turn a page, and we use this number to get started a Vigenère cipher. And that is proven theoretically unbreakable unless you kill the spy and you get the pad. But theoretically, if that doesn't happen, then you can keep working like that. But it's not great because you have to start somewhere that you both share a pad, right? You can't set this up remotely. If that pad is lost, then you have to travel back to England to get a new pad of paper. Okay. Then the Enigma machine was patented by Arthur Scherbus, and that was a big advance in that it's not theoretically, again, sort of the algorithm is just a whole bunch of Caesar ciphers put together and some mixes and transpositions of characters, but it's robust enough that it took quite a while to crack by some Polish mathematicians who did much of the work or a lot of the work, and then Alan Turing and Bletchley Park figured out how it worked, and they were able to crack, and that actually sort of like turned the wind of the war of World War II. Now, in 1949, you might now the name Claude is quite common nowadays. That refers to Claude Shannon, and in 1949 he formalized what's right now known as mathematical cryptography as a field, as an area, and did a bunch of work. And then some years later, we have the first instances of what we call public key cryptography. As I said, the one-time pad that has the problem that you have to be in the same place to get the same pad. So how can you set up a secure method of communication when you are far away and you have to do a transmission to even get started? That's what public key cryptography is trying to figure out. And even though it was published, like the first type of public key cryptography was announced by Diffie and Hellman, GCHQ, so the British NSA basically, they already had invented something equivalent to it in secret. And then we had RSA come in, and then in 1985, simultaneously Koblitz and Miller independently proposed elliptic curve cryptography. And much recently, the uncle of my graduate program roommate, so as I said, it's very important the people you meet is Peter Shor demonstrated that quantum computers could efficiently factor integers, threatening RSA and related systems. So that's where I'm going to stop that story, in that if there are quantum computers, there is a bunch of things here that would be outdated. But as I said, elliptic curves, I think, have a role to play even in a quantum world. So here we are going to try to concentrate on the elliptic curve cryptosystems. This is the start of Koblitz's paper. By the way, if you've seen the poster for CT&T, there are a couple of equations in there, a limit and some equation. They come from Koblitz's paper, a Miller paper. And they're very readable papers. Like if you've seen if you've seen some course in elementary number theory, you can read the papers and see what they're doing. It's not, or if you know a little bit about elliptic curves, they're very nice papers even today to read. You can see this was from 1987, and then Victor Miller published a use of elliptic curves in cryptography, also introducing, as you can see, that is introducing a Diffie-Hellman scheme instead of for z modulo p, instead of working modulo p with integers, works with elliptic curves, and he says that it appears to be about 20% faster. And it is faster, even though elliptic curves are, is more complicated to do addition on elliptic curves than to do addition modulo p. The size of what the keys are, the size of the primes you have to use, or the size of the keys are smaller for the same amount of security. So you don't have to use as much resources for the same amount of security. And then Lenstra also published another paper that is called Factoring Integers with Elliptic Curves, which is another thing, one of the other things that I want to show you of how to use elliptic curves to do factorizations of integers, which helps, for example, in breaking RSA. RSA is based on having some large product of two primes that nobody knows what the primes are. So this would help in trying to break that kind of algorithm. Okay, so I'm going to start with some elementary number theory just to remind you. So we're going to be fixing a prime. In many cases, I'll try just to use maybe something like 7. I think 73 for some reason will appear a lot in my slides. 4001 and 4003 are a favorite pair of twin primes, so they will also show up from time to time. And then n is a natural number, but we will often think of n as a composite number, so something like 6 or 35 or 4001 times 4003. Now we are going to be using congruences. We say that A is congruent to B modulo n, and n divides their difference. And here's a couple of examples of congruences. Do you know who invented congruences? Gauss. What year was that?
I know it was in the Christianis, but I don't remember what year.
So Gauss introduced, of course, the concept of congruence was already maybe in like Fermat, and I mean, not congruence itself, but he was working with the residues, was he not? Okay, so the seed of congruence was in the air, but it was Gauss in 1801 that the very first page of Disquisitiones, he sets up congruences. And if you have not read Disquisitiones, it's a wonderful book. You might think like, oh my goodness, 1801, no, there's no way this can be readable. It's wonderful because it already reads as a modern text. And the very first page, you can see it here, and he's using that symbol. He defines congruence. He uses examples, like numerical examples, some like congruence modulo 11, some congruence modulo 5, and then he starts proving things about congruences. That alone, once you have the right notation, then you can do a lot of stuff. So we are going to be working with the integers modulo p. The integers modulo p, you can add them and you can multiply them, but we're actually more interested in this case in the multiplication structure of the integers modulo p. So we are going to talk about like the units modulo n. So the units modulo n are those numbers between 1 and minus 1 that the GCD of a and n is 1, and those are the units. These are numbers that have multiplicative inverses. So not if n is composite, then not everything satisfies this, so not everything is a unit. But if p is a prime, then you do have that 1 through p minus 1. Every non-zero number modulo p is a unit. So we have this turns out that z modulo p, which we will many times just write as fp, is a field. Okay, because every non-zero element modulo p is invertible. It has a multiplicative inverse. So it works just like Q, R, or the complex number works, but the benefit is that it is finite, so it's amenable to computation. By the way, we will do a lot of computations, so some of these I will throw in some examples and things for you to do. Eran will be running a mini course on Magma and databases. And along the way, either through his course or during problem sessions, I'm happy to sit with you. And if you've never worked with Magma, say, or Sage, I'm going to ask you some questions that you can do some by hand, but it's much easier if you start learning how to use some of these computer tools so that they help you in doing those computations. Okay, so the size of z modulo n z cross is what's called the Euler phi function. And as you can see here, I've actually listed every unit. So phi of a prime p is just p minus 1. But phi of a composite number, well, there are some formulas that you can learn to compute values of phi. So here are some examples. Here's an example that modulo 7, 3, and 5 are units because 3 times 5 is 1. So 5 is the inverse of 3, and 3 is the inverse of 5. 2 and 18 are units, modulo 35, and they're inverses of each other. And then we can start raising numbers to powers. So if you start with 2 modulo 7, 2, and then 2 squared is 4, 2 cubed is already 1, 1 modulo 7. And it turns out you can prove, I don't know if you know how to prove this, but if you have a unit, modulo n, then there is a number that if you raise it to that number, you get 1. So you start taking powers, you'll get back to 1 at some point. Do you know why that is true? Well, that will be an exercise, and you can remind yourself of like, how would we prove that? So this, we say that the order of 2 is 3, because after the third power, I get back to 1. But the order of 3, you can see that is 6. Okay. The key here, though, the key thing to realize is that when the order of 3 is 6, since there are 6 units modulo p, I get back every unit as I do those powers. But I get them back, maybe I shouldn't do a set, but more like a vector. I get them back in a funny order. I get 3, 2, 6, 4, 5, and 1. So I do get all of them, but they are somewhere somehow randomized. And that's already immediately should trigger like, this is cryptography. Because if I can't say ahead of time, well, I can, because I can take powers of 3 and know exactly what that is in this case. But if it looks like the output seems random, then you should be able to use that to build some sort of cryptographic system. And that's exactly what we do. So, so let me just keep going with the definition. So if we have an integer n and another integer that is relatively prime to n, so that it is a unit, or the class of a modulo n is a unit modulo n, then we define the order to be the smallest positive natural number such that a to the n is 1 modulo n. And again, you might think about like, why does that happen? Why couldn't it have like some sort of loop that never hits 1? So the order, what we've seen is that the order of 2 modulo 7 is 3, but the order of 3 modulo 7 is 6. And we're very much interested in these, that through powers, consecutive powers, we actually retrieve every unit back. Now, here's a question for you. So what is the order of 2 modulo 4003? How would you compute that? You would use, as a shortcut, the theorems of Fermat, Euler, and Lagrange. By the way, another thing that helps very much is that to compute powers of numbers modulo 2, so there is something that is called the fast powering algorithm. So if you want to compute some power of 2, say what is 2 to the 4002, you don't have to, if you just want 2 to the 4002, you don't have to compute 2 to the 1, 2 to the 2, 2 to the 3. What you do is you write 4003 in binary, and then there is a way to just repeatedly square your output to get sort of like what are the possible powers of 2 to the numbers that appear in the binary expansion of 4002. So I'll set up a problem for you to explore that. Okay, So why do these theorems help? First of all, we have Fermat's little theorem. And Fermat's little theorem from this point of view is telling you that if you have a prime and you have an integer that is relatively prime to p, then a to the p minus 1 is 1 modulo p. That doesn't mean that the order of a is p minus 1, but it does tell you, maybe this is more a corollary than sort of like how usually we state Fermat's little theorem, but it does tell you that the order of a has to be a divisor of p minus 1. And there are not so many divisors in general of p minus 1, so you can actually check like what are the divisors, say, of 4002 in the previous example, and the order has to be one of those numbers. So you could just try out. You don't have to try every single power of 2. You can just try what are the divisors of 4002 as possible orders. This, by the way, this will come back. Euler's theorem, Fermat's little theorem will come back when we talk about factorization. To do factorization and to set up something like RSA, we're going to need very large primes. And to compute like large primes that are 2048 bits, something like 2 to the 2048 in size, we actually don't have very good tools on how to do that. So we use things that are what's called pseudo primes. We'll talk about how to compute pseudo primes, and this is one test for something being prime. We can use Fermat's little theorem to test primality, and then we do things that are much more sophisticated to test primality. We'll do that later. By the way, please do interrupt me if you have any questions at all. I would love to entertain them during the lecture, okay? Any questions so far? We're good? Okay. Euler's theorem tells you if you're working modulo n and you have a unit modulo n, then it tells you that the order of every unit divides phi of n. So again, computing the number of elements in there tells you that what are the possibilities for the order of a unit. More generally, those two theorems are incarnations of Lagrange's theorem, because z modulo p, so here what's happening is that we have a group in the background, which we are working with the group z modulo p cross. Here we're working with the group z modulo n z cross, and then we can replace those by an arbitrary finite group G. And what Lagrange tells you is that if you have a subgroup of G, then the order of the subgroup divides the order of the group. And for example, if you have an element, then you can look at the subgroup generated by A. So if G is, we think of G multiplicatively, then this is E and G, A, and A squared and A cubed up to the order of A, so up to n minus 1, because at the order we would go back to E. So that is that set if the group is finite. So it tells me that the order of the group divides the order of the subgroup. The subgroup generated by one element divides the order of the group, and therefore the order of the element, which is the size of the group, this is n elements over here, then the order of the group divides the order of the element divides the order of the group, which is exactly what Fermat's little theorem and Euler's theorem are telling you. So you could think of that in the general setting of a group. Now, I want you to, it depends on what level you are, but I want you to start thinking about everything that we're doing. What we're going to do is I'm going to explain to you how to do cryptography in one group, z modulo pz cross. Then we're going to switch it to do cryptography over an elliptic curve. But what I want to do this week is to just like, okay, let's pick groups. Let's pick other groups, and let's try to do cryptography on other groups and see what happens. Because this is an arithmetic geometry course in disguise, I will want you, if you know what this is, if you know what a Jacobian is, if you know what an abelian variety is, if you've ever heard of these, or if you haven't heard of them, we can teach you what they are. I want to try to set up Diffie-Hellman on an abelian surface. But if you don't know what those are and you don't want to get into that, what about some other groups? I don't know, some like dihedral groups. Can you do cryptography on dihedral groups? Can you do cryptography on some matrix groups? Take some subgroup of matrices that's 5 by 5 over your favorite field. Probably you want finite fields. But in Magma, you can do exact arithmetic on rational numbers. So what happens if you do that? Well, you'll see that there are implementation issues. So if you pick up some groups, there is a reason why we landed on elliptic curves, and why even like going up to abelian varieties, it's counterproductive. But I want you to try it out and see what happens. And why is that not the case? Why are we not using other groups? Okay. So now for z modulo p z cross, we have a theorem of Gauss, again in Disquisitiones, because that book is a gold mine. We have that, in fact, that group is cyclic. What it means is that there is always a unit of order p minus 1. So there is always a unit that the powers of that unit will retrieve every unit. Okay? And that's awesome, because that means that I can actually pick any prime, find one of these roots of unity, or one of these what we call primitive roots, and do the powers and get some sort of like randomized order. It's not random, but it looks random and it feels random, and there's some like theorems that say something like that. So we can do that for every prime. Now the question is how to find these primitive roots. So that's a little bit of a problem. So by the way, there's not just one. There are phi of p of them. Okay, so once you have one, if you know there is one, there's actually phi of p, and we do know there is one because of Gauss's theorem. And the other part is that, so yes, there is a unit of order p minus 1. Z modulo p z cross is cyclic. And that means that as abstract groups, this group is isomorphic to this cyclic group of order p minus 1. But the key is that you know how mathematicians love to say that there's a canonical isomorphism. If it's like, when I don't know if you've seen the proof that, one of my favorite proofs, that a vector space, a finite dimensional vector space, and it's the dual of the dual, they are canonically isomorphic. There is no such thing here, because you have to first find a primitive root. And finding primitive roots, we have methods on how to do it, and if you assume things like the Riemann hypothesis, then we have bounds on how long is it going to take you to find a primitive root, but we don't have a method that will give you primitive roots. There is, if something that you want to explore also this week is something called Artin's conjecture. Artin's conjecture tells you, for example, that the number 2 should be a primitive root infinitely many times. But we don't know how to prove that. So just finding a primitive root, there are methods, and as I said, you can just pick a number and start. And if you read an elementary number theory textbook, there is methods that help you just build out of units that are not primitive roots. There are methods to build primitive roots, but it's not an easy problem. So here, for example, we had a primitive root. The powers of 3 modulo 7, because 3 has order 6, is a primitive root. And one of the questions for you is to find a primitive root modulo 4001. Now you can ask Magma and say, what is a primitive root modulo 4001? But I would like you to try sort of by yourselves. You can do a little bit of calculator use if you want, but try to find a primitive root modulo 4001. 2 is a primitive root modulo 4003. And as I said, that is nice because then the powers of 2 will go through every unit modulo 4003. But it's not great because, of course, the first ones at least are very recognizable. I know that the first ones that will appear are 2 and 4 and 8 and 16 and 32 and so on until I go above 4003, and then sort of like the quote-unquote randomness kicks in, right? So it's actually better because I have more primitive roots. If I have 1, there's a formula. Once I know 1, I actually do have a formula for all of them as powers of 2. So I can actually find a primitive root where sort of the randomness kicks in immediately, meaning that if it's a primitive root whose square is already bigger than the modulus, then that one is already starting to look somewhat random. And I've done that. So here are the first few powers of 65 modulo what? 4003. And you can see that it's just like, you know, it's very hard to tell in what order are these coming. Well, I know I can start taking powers of 65, but that's the issue, that you would have to start taking powers of 65 and do all the powers of 65 modulo 4003. Now change 4003 by a prime that has, you know, a million digits. Now we're talking, and it's going to be very difficult to figure out what the, you know, at what point one given number comes in. And that is exactly what the discrete logarithm problem is built on, which is, here's a question for you. 65 is a primitive root. What is the first number A, the first non-negative number A that gives you 2026? 2026 is a unit, so it has to be a power of 65. How can we tell? Well, do you know? Is anybody here? So it is 85. But try sort of by first principles, try to figure out, well, 2 has to show up also as a power of 65. How do you figure out what power of 65 gives you 2? Okay, so that is what's called the discrete logarithm problem, and this is the discrete logarithm problem modulo p, which is sort of like the first type of discrete logarithm problem that showed up, and the problem is given a prime p and given a primitive root and given another unit, then find the x such that g to the x is congruent to h modulo p. So that is called the discrete logarithm problem, and it's known to be hard. It's not hard in the sense of NP hard, but it is a computationally hard problem. And by the way, they call this x is the logarithm in base g of h. Okay, sort of abusing notation from real complex analysis. We usually call them logs. What is the log in base g of h? Okay, so that is the discrete logarithm problem. And as I said, some of the algorithms that first came into the picture, the Diffie-Hellman algorithm, the Al-Gamal cryptography, are based on this being hard. But as I said before, I want you to start thinking, you know, like Victor Miller or Koblitz did. It wasn't, I mean, it was a great idea at the time. Now you think about it, it's like they just changed the group. That's all they did. So let's change the group. So if you have any group, we can set up a discrete logarithm problem for G, which is take a group, probably a finite group, but maybe the group itself doesn't have to be finite. It just has to be the order of G has to be finite. So you don't even need a finite group. You just need the group generated by G to be finite. And then, so take a G, take an H, and then the problem is find if it exists. In the previous problem, we always had, because G was a primitive root, we always had that some power of G gives me H. So there is always an X. Okay? But here, a priori, you can set it up so that not everything in the group is hit as a power of G, because if you don't want to restrict yourself to cyclic groups, as I said previously, I said, why don't you try a dihedral group? of order 2 times p, where p is a very large prime. That is not cyclic, so you don't want to include that, because not every group element will be a power of a single element, otherwise it would be cyclic, and the Hilbert group would be a billion. So the problem is now, if it exists, find an x such that a power of g is h. We will again call it a logarithm, or show that no such x exists. Maybe that's part of the message. Maybe that if it doesn't exist, maybe that is it has something to do. In any case, and then the question that I'm going to bring up a bunch of times is, let's replace z modulo pz by other groups. For example, elliptic curves. So that was the idea, to change z modulo p z cross by some other group where the group structure itself is already part of the problem. The addition of an elliptic curves, the addition or the multiplication of 2 elements modulo p is very simple. But the addition itself on elliptic curves, it's already kind of obscure what you're going to get if you have 2 numbers, and there is already some computational aspects to computing what is the addition, in this case, of 2 points. So we are going to take this group modulo p and replace it by the points on an elliptic curve over a finite field. So what is an elliptic curve? In principle, elliptic curves can be defined over any field. So f can be q or r or fp. And I think in 2024, I gave a mini course on elliptic curves, concentrating mostly over q. So you can go back if you want to learn more about what happens over q. But you can generate elliptic curves over any field. And here we're going to be thinking about fp. But there's other fields. You can think about fq, where q is a power of a prime p. And we could try to do that too and see what happens. That's a different group that you can think about. So an elliptic curve for us is just going to be a planar curve that's given by a cubic polynomial in 2 variables, f of x, y equals 0, and such that E is projective, smooth. So we think of elliptic curves as projective curves. Many times I'm not going to worry about the projective part of elliptic curves. We're just going to give them in an affine plane and not think much about the projective properties. But it has to be projectively smooth, and it has to have at least 1 point with coordinates in f. So for example, we can think of, I think I have it in the next slide. Here is an elliptic curve. So this is not a laser. This is a cubic in 2 variables. And you can see that that cubic is smooth. So you can find the tangent line at every point. It has a well-defined tangent line. There is a point over any field. So this is actually field-free because I can define this over any field. This could have been Q, R, or FP. That point is on any field because 1 and 0 are elements of the field. And I can do these algebraic operations over any field. So that is an elliptic curve. And as I said, you have to worry when you have an elliptic curve that they are projectively smooth. So what that means is that we actually think about them in projective coordinates. This elliptic curve would have these projective coordinates. And you have to work with patches and just make sure that every point, even those points at infinity, there is a smoothness at infinity. If you want to explore that, we can talk about that during problem sessions. How do you prove that this is smooth at infinity? But we're not going to do much of that because over fields, at least if the field is of characteristic bigger than 3, if it's characteristic 0, or the characteristic is bigger than 3, then every elliptic curve can be written in what we call a short Weierstrass model. Okay, and they can all be written in this form. And here there is a point. It's not an obvious point because there is a point The point that is fixed is the only point that is at what we call infinity in projective coordinates. So this is a point that is an infinity. You can think about it as a point that is at the intersection of every vertical line. Okay, every vertical line ends up pointing, touching at infinity at one point, and this is the one point. And that point actually belongs to the elliptic curve. So once you have that, then you don't have to worry. These models, as long as this is true, these models are smooth. Again, we're not going to do cryptography over F2 or F3, so you can forget about those and then just have models of this kind. And those are elliptic curves. Those are what's called a short value stress model. But as I said, it's actually important to know that you can do elliptic curves over just with any cubic form that is non-singular and projective. And actually it would be interesting to also set up somehow cryptography that is native to an elliptic curve in that format. Yes? Oh, because it would have very few points. If you have over F2 over F3, there's at most something like over F2, the projective plane, or the affine plane in F2, it has 2 times 2 plus maybe 1 point at infinity, so maybe there's just 5 points. So there's not enough points to actually do cryptography. Here, we're going to do cryptography over Fp with P very large. Well, you'll see my slides, large for me is 73. But again, you should think about some prime that is of the size of 2 to the 2048. You know, that big of a prime to do actual cryptography. Those are, I think I checked, that's the current standard is like use a prime that large to be safe. And to be safe, you actually have to also be careful what elliptic curve you use, because the structure itself of the elliptic curve can contribute to be amenable to some attacks. So there are standards, I think it's called NIST, NIST standards, that give you some idea of what elliptic curves to use for what primes to be safe. Those have been studied to be, to survive all sorts of different attacks. On the other hand, one of our sponsors, NSA, provides those as saying like these are safe, but other people think like NSA has had enough time to actually pre-compute every single point on those elliptic curves, and they could have tables that when you are using them, they can just like read all the messages straight from that table. So just be careful who you listen to for advice of like what curve to use. You might be better off picking your own if you know what you're doing. Yes?
Is there a quick intuitive idea to understand why we need those additional conditions for a cube plus 1 squared?
This? Yeah, so this is, that's a very good question. So why this condition? This condition is that is related or is straight up the discriminant of this cubic. If this quantity is 0, what happens is that 2 of the roots of that cubic are the same. Okay, so actually that's a very good segue to the next question. So let me repeat the question. Is there an explanation of why this condition? And the condition is, again, that the discriminant of this cubic polynomial is non-zero, because if it was 0, 2 roots would be the same. And when 2 roots are the same, we get singularities. So for example, in this equation, 3 of the roots are the same, and then we get a cusp. So it's not smooth at that point. If 2 roots are the same, then we get what's called a node. So it would look like this, like that. There would be an intersection point there where the 2 roots coincide, and that would be, for example, the equation y squared equals x cubed minus x squared has that problem. That is not an elliptic curve because it's not smooth at that point. I can't pick a tangent line at that point. So these are not elliptic curves, not and not, but this is a beautiful example of an elliptic curve. That's another beautiful example of an elliptic curve. Okay. Much of my research is in elliptic curves, and particular elliptic curves with complex multiplication. With these, both of them have exactly that property. So that's why, in part, I consider them to be beautiful. There's a question here for you to think about. Why is y equals x cubed not an elliptic curve? Okay, so you can answer that in the homework. Okay, so the property that makes elliptic curves really nice and useful is that if I define, first of all, you take an elliptic curve over a field f that is given like this, so this is nice and smooth, and then we set up this set of all points, so pairs of points that satisfy that cubic, and the point at infinity, then we can define an addition on those elliptic curves. So we can define an addition, and the addition in this setup, the graph looks like this graph in orange, and the addition is that you trace lines from P to Q, and then there is going to be a third point of intersection. It turns out that that third point of intersection, because this is a cubic, that third point of intersection is again in the same field. It doesn't go into some like extension of the field, and then you do a reflection just so, for example, it helps to do this so that the law is associative. So you take this one point here to be the addition of P and Q. So that makes the points on the elliptic curve a group. And for example, and here's an example that if you take the elliptic curve y squared equals x cubed plus 1, and you take these 2 points, then you can use that to actually find more points on the elliptic curve, because you can do the line from P to Q that passes through a point R, and here is the computation. R would be in the intersection of the line and the curve, and you can figure out what are the roots, and you can actually see that right here, these equation that I get, now I get an equation, a cubic equation in one variable. That equation has already 2 roots, because I know x equals 0 and x equals, x equals minus 1 and x equals 0 have to be roots. So now I have already two roots that are rational, so the third one will also be rational. And I get a point 2, 3, and the addition is down here. The addition will be 2 comma minus 3. That is, oh, by the way, there's also a graph that appears in the poster for CT&T 2026, and it is actually given by that elliptic curve. Whoa, don't do that. That elliptic curve, y squared equals x cubed plus 1, and you take the point 1 comma square root of 2 is in there if you consider this elliptic curve over the real numbers, or if you consider this elliptic curve over a field where 2 is a square, or 2 is not a square, where 2 is a square, then the square root of 2 is in that field. So for example, if you're looking at F7, then 2 is, well, 3 squared is 9, so 3 squared is, the square root of 2 is 3, right? So, so that point would be in F7, and well, this is not a very good representation of an elliptic curve over F7, but in any case, what I wanted to show you is that I started with P, and then I started doing multiplication or addition, repeated addition of P, 2P, 3P, and then 5P's over here. Already you can see that there is some mixing happening in this addition that immediately should scream, this is something that one can exploit for cryptographic reasons. Okay, this is one visual representation of this mixing of where the points land. You know, if you already look at like how would I have figure out where 25P would land, I can't sort of like ahead of time know where this is going to happen. But the coordinates themselves also represent that there is some mixing in the coordinates that works like the powers of a number modulo P, the powers of a root of unity. By the way, there is, and if you, so this is not just a group, it's an abelian group, and there's a group law. Here I have written the equations that that define addition on an elliptic curve, so you can actually do it. It's nice to do it at least a couple times by hand, by actually looking at the coordinates, computing the line that goes through P and Q, and then computing intersections and so on. But you can automate that and find these kind of formulas every time. And these formulas, as long as if you're working over a finite field, they still work. They still work. So you can still use these formulas because you can see, for example, we're going to, if you're over a finite field, then this is 0 or invertible. This is 0 or invertible. And if these are 0, then something has happened already that is covered by some other case. So you can do these also over a finite field. Now, so this is not an elliptic curve. It turns out that this is not an elliptic curve over F3. Do you know why? The discriminant vanishes. So what happens is that it doesn't look like it because we don't think about, we know that these roots are different in the complex numbers, but over F3, there is a collapsing of roots, and all of a sudden that graph, if you imagine it in F3, then there is some intersection of, there is some node in there. But over F7, it's perfectly fine. It turns out that that discriminant does not vanish, and therefore, this is an elliptic curve. And the question is, what is that group? What are actually, what does that group look like? So we're going to be talking about that probably. I'll start here in the next lecture. But it turns out that the points, you can compute what points are there by, well, what are the possibilities for points? That's also the beauty of working over a finite field. You can pick what possibilities are there for x, 0 through 6, and then check if they are actually coordinates. So 0 cubed is 0 plus 1. That is a square, so the y coordinates are plus or minus 1. What about 1? If I take 1, 1 cubed is 1 plus 1 is 2. And 2 over F7, as we said, is a square, is the square of plus or minus 3. So that gives me 2 points, 1 comma 3 and 1 comma minus 3. Those are points on F7. And so on. So you can just go through the entire list and compute all the points. So this is the group. It's a group with 12 points. But if you've done some abstract algebra, then that is an abelian group with 12 elements. What are the possibilities? What group could this be? It could be there are two possibilities. It could be that it's cyclic and it has z modulo 12, but because there's a factor of 4, it could be something like z modulo 2 cross z modulo 6, right? So one has to figure out what kind of groups you get. And I'll start with that count next time. So we are going to, there are some results that will help us try to figure out what groups we can get. So I'll stop here, and then we'll continue with a little bit of elliptic curves next time, the DLP for elliptic curves, and then we'll start doing cryptography using the Diffie-Hellman. Okay? So thank you.